Okay, as a review of what we've done so far, we've learned that the magnitude of the force between two objects of mass, big M and little m, can be written in terms of the product of the masses times g divided by r squared, and that force is always attracted. We also learned how to calculate the magnitude of the gravitational field produced by some point particle or a spherical object. Anything that has spherical symmetry, we write it as g equals little g equals big G times the mass divided by r squared. And that field is always radially inward, meaning the field is always directed towards the source of the field. The direction of the field vector always points toward the source of the field. The potential energy is written as minus big G times the product of the two masses divided by the distance between them. And this equation assumes that the potential energy is zero at infinity when the objects are infinitely far apart. We also calculated the velocity for an object going in a circular orbit, whether it's a satellite orbiting the Earth or the Earth going around the Sun, which is approximately circular. We're gonna assume in our problems that we're dealing with circular orbits. I know that you have that equation there, and it's easy to memorize, but I expect you to know how to derive it. On the final exam, I expect you to know how to derive that equation, because you probably won't have it at your disposal. We also calculated escape velocity. Now, the escape velocity, if you look at the two equations for the escape velocity in circular orbit, we got to be careful. The little r in the circular orbit equation is the radius of the orbit, whereas the big R in the escape velocity equation represents the radius of the body that you're trying to escape. For example, the radius of the Earth or the radius of the Sun, for example. But the little r represents the radius of an orbit. The orbital energy, whether the object is really going in a circle or, for example, in an elliptical orbit, can be written as minus big G times the product of the two masses divided by 2r. You should use this equation as a reference to see whether you're solving the problem right. You need to be able to derive that. So in an exam, if you're given an equation where you have an object going in a circular orbit, I really don't want you to use that equation. What I want you to do is be able to derive that equation. Otherwise, you'll lose points. How does the physics here relate to that of the electron in an atom? In other words, how does one change the electron orbit in an atom? And we use the same ideas. We use the same ideas we talked about. If you want to change the orbit of the atom, the electron in the atom, you have to add energy to it to change the orbit. When you change the orbit, you're changing the angular momentum of the electron, and you're changing the energy. Let's apply these ideas that we've learned so far to our solar system. In fact, what I want to look at is Keplers laws. Kepler was able to deduce three important laws about the orbit of the planets around the sun from basically observations from various astronomers. He came up with the following three laws from his observations. They were called laws because at that time there was no theory that allowed him to derive these equations. One of them is that the orbits of the planets are all really ellipses, with the sun at one of the foci of the ellipse. When a planet orbits the sun, they will sweep out equal area for equal time. So we're going to derive this equation. We're going to derive this idea using Newton's law of gravitation. This is really a consequence of conservation of angular momentum. In fact, we're not really going to apply the law of gravitation specifically. We're going to write this in terms of conservation of angular momentum. And then if you take the ratio of the period squared over the radius cubed for the orbit of a planet around the sun, it's equal to a constant. Like it's always equal. It's equal to a constant for orbits around a common center. So, for example, even if you're talking about a satellite orbiting the Earth, the ratio of t squared over r cubed is a constant. Just that constant is different depending on what the satellite or planet is orbiting. I want to look at Keplers' second law. And I'm going to, because the picture is a little bit more challenging to draw, I'm going to rely solely on a PowerPoint for this derivation. And I'm not going to write anything on the board here. So let's consider a planet, which is that red object that you see here. This is the planet. Here's the sun at one focus. The planet's orbiting around the sun. And I want to consider the torque acting on the planet. Now, we think about it, the force vector is along that white line joining the planet and the sun. The r vector is also along that same line joining the two planets. Those two vectors are in opposite direction, but the sign of the angle between them is 180. The sign of 180 is 0. As a result, the torque is 0, and angular momentum is conserved. So when you have, for example, a planet orbiting the sun, the angular momentum is conserved, and so is the energy. Let's consider the motion of a planet at a couple points. And what I've done is over two pairs of points. I'm going to look at the area swept out. For example, the area swept out as the planet goes from this location to this location. In fact, let me change the color of my laser pointer. Oops, 1 second. Sorry for the technical issues. Okay, I guess I gotta stay with this color. Let's consider a planet going from this point here all the way to this point, and a planet going from this point here to this point. I want to look at these areas swept out by the planet as they go from between these 2 points here and between these 2 points here. What I want to look at is the rate at which the area is swept out by those planets as they orbit, they proceed in their orbit. So here's the sun, and here's the r vector, which goes from the sun to where the planet is at. I want to consider the following. I want to consider how far a planet moves in a time delta t. And I'm going to assume delta t is very small. And now I'm going to look at basically between 2 points, A and B. So I'm going to look at a planet that goes from this point to this point, okay? I'm going to assume that the elapsed time is small. So even though this is an arc, if the time is small, this arc really becomes a straight line. So think of this as a straight line, and think of A, B, and S as the vertices of a triangle, okay? And we're going to look at the area of this triangle. And see what we can learn from it. The distance from A to B, remember, is just a straight line. We're assuming the time interval is small, so this arc length is really a straight line. And the length of it is determined by the product of the velocity, which will not change very much there, times the time interval. The velocity doesn't change very much because our delta t is very small. In fact, we can make it infinitesimally small if we wanted to. So if we look at our triangle ABS, the height, the altitude of the triangle is given by this red line you see here. In fact, let me highlight it again. This red line here is the altitude of the triangle. The velocity vector is tangent to the orbit, so here's your velocity vector, and then you have your r vector, and then the angle between those two vectors is theta. Well, if you notice, you have between this line and the velocity vector, you have vertical angles. So where you see my pointer, that angle is also theta. These are vertical angles, so this angle is also theta. So the height of this triangle, this is a right triangle here, the height of this triangle, the red line, is just going to be AB sine of theta. Okay, so this height is going to be AB sine of theta, and the area of this triangle is basically half the base times the height. So the base's length is r, the height is h, but h is AB sine of theta. But AB is V delta t. So we can write the area swept out in the time delta t as 1/2 r times V delta t times the sine of theta. Now, think about what that product of r times V represents. What I'm going to do is, the next step I'm going to do is divide both sides by delta t. And really what I'm looking at is the rate at which the area is swept out is going to be equal to 1/2 times r times V times the sine of theta. Think about what this product, r times V times sine of theta, represents. Well, let's go back and remember what angular momentum is. Angular momentum is r cross p, and its magnitude can be determined by the magnitude of r times the magnitude of p times the sine of the angle between r and p, where p is mv. Well, if you look at what we had before, the RV sine theta is just L over m. It's the angular momentum over the mass of the object. So our delta A over delta T is just the angular momentum over twice the mass of the object. It's a constant because angular momentum is conserved during the orbit because we said that the torque was equal to 0. So that means that we have equal areas per equal time. So what does this mean? Let me go back to the drawing. When you are closer to the planet, r is smaller, but v will be bigger. If angular momentum is conserved, as you make r smaller, v is going to be bigger. So when you're closer to a planet, you're going to move faster. So you sweep out this area. When you're far away from, not planet, to the sun. So when you're closer to the sun, you're going to move faster. When you're further from the sun, you're going to move slower. And so this area over the same time interval, this area you see here and this area you see here are going to be equal over the same time interval. And that's because when you're closer to the sun, or whatever the planet's orbiting, you go faster. And when you're further away, you go slower. So Kepler's second law is a consequence of conservation of angular momentum. Now Kepler's third law is actually fairly easy to derive. And so I'm going to go on the board. Oops. I'm going to go on the board and derive Kepler's third law. My PowerPoint died there, so I'm just going to derive Kepler's third law. Okay, so I apologize. My PowerPoint just died in the middle of the video. I'm not going to start over again. I'm going to show you Kepler's third law because it's pretty straightforward. We don't need the PowerPoint for this. Luckily, the PowerPoint quit at the right time. Okay. Let's consider a planet going a circular orbit around the sun. Okay, I know they're not circular, but let's pretend it's circular. This is going to make the math easier. One can show that this is true even for elliptical orbits. But let's not worry about the elliptical orbit. Let's just do circular orbits. If you have a body going around the sun, or a body orbiting some other body in a circular path, that gravitational force is producing a centripetal force. It's producing acceleration in a circle, and we can write our equation. We're basically applying Newton's second law. This is our MA from Newton's second law, and then this is the gravitational force of attraction. Now, if you're going in a circle at a constant speed, V can be written as the circumference of the circle divided by the period. So let me put this in here. Oops, it's an R, not an R squared, sorry. So we have this term is equal to this term. Let me write it down here. Now, I can simplify this by I can get rid of these M's. I can get rid of one of these R's. And what I'm left with is the following. This leads to G big N over R squared equals I squared. I'm going to bring this R down here. And then I write T squared. I'm going to bring the T squared up here. And then get this constant. The ratio of T squared over R cubed is equal to this constant. 4 pi squared divided by the gravitational constant divided by the mass of the object the planet is orbiting. This is all a constant. If this is the mass of the sun, then this number turns out to be 2.97 and it's 10 to the minus 19 seconds squared per meters cubed. This is only valid for this, or this numerical value is only valid for something orbiting the sun. If you have a satellite orbiting the Earth, then you'd have to put the mass of the Earth here to get a different value. Now, here's the cool thing. If you write the period of the planet orbiting the sun in years, in the distance in astronomical units. Now, by the way, I know the orbits are elliptical. If you want to do it for an elliptical case, this distance is the length of the centimeter axis of the Earth. If you write this in astronomical units, 1 astronomical unit is basically the distance between the Earth and the Sun. This ratio is 1 for all the planets in our solar system. So if you write T in years and R in astronomical units, this ratio is 1 for all the planets in our solar system. It's kind of interesting. If you don't use those units, then you just say T squared over R cubed is a constant, it's this constant. You can just write it as C because we really don't care. When we're solving problems, we don't care what that value is. What we care about is this. Let's say you change the orbit of a satellite and you want to know the new period. Okay, this ratio stays constant. If the satellite's orbiting the Earth, that ratio is going to stay constant. You change the orbit to some other value. You change the orbit to some other value. You can solve for this because this ratio is a constant. And you can say, okay, well, T2, solve for T2, and you get your result. You don't have to know this numerical value. You just need to know that this ratio is a constant for that satellite orbiting the Earth, or for the Earth orbiting the Sun. That ratio is a constant. That's all you need to know. And so those are Kepler's 3 laws. And so this law we were able to derive using the law of gravitation. The second law we're able to derive really from conservation of angular momentum. And so when Newton developed his ideas in physics, he was able to actually derive the 3 laws of Kepler. Where Kepler himself, he was able to use them just by analyzing data and looking at trends.